Weak acids and bases, everything else. If it's not one of these, it's everything else. So weak acids and bases, which is what we're going to be dealing with for most of the rest of this chapter, they only partially dissociate or form ions, if you prefer, in solution. For our purposes, this would be any acid or any base that is not one of the 14 compounds that I just gave you as strong. If I'm going to give you something that's strong other than what's on there, I will give you the formula and say a strong acid. So I will tell you, if it's not strong, you assume it's weak. So in order to figure out stuff with these, you have to use equilibrium properties. So here, we're talking about equilibrium properties, so the equilibrium constant K comes back. I told you it wasn't going away. K is everywhere. Now, we will call this, I don't generally italicize it because it will usually have a subscript, a sub-letter associated with it. So if it says Ka, that's just how you say it, you just say Ka. That is the acid ionization constant. So, we have all written equilibrium expressions. We're going to do the same thing. So, if you're running your reaction where you actually have water in it, you know, so this is your acid, water is going to be the base, water becomes the conjugate acid, A becomes the conjugate base. Or if you want the shorthand notation, take water out of it, this is also acceptable. So, again, remember K equals products over reactants, right? And we have to deal with the stoichiometric coefficients sometimes. Usually with acid bases you don't. With acids you don't, with bases you might. So, Ka here could be, according to, if we're using this first equation, concentration H3O plus, concentration A minus over concentration of HA. We do not put water because water is a pure liquid. So water does not have a concentration. For that reason, most people prefer, myself included, the shorthand notation of just writing the dissociation equation. So if you're using that, H plus, A minus, HA. This is an A, not a delta. It's just according to the second equation. Oh. It just depends on either what the problem gives you or whichever notation you prefer. I'm giving you 3 ways to write Ka and you pick the one you like. Or, I don't know anybody that's going to like this one, but if you do, awesome. Or you can say concentration of the conjugate acid, concentration of the conjugate base over the concentration of the acid. All of these mean the same thing. They're all saying the same thing. Pick the one that you like.
What if you have a base, or would it be conjugate acid over conjugate base? Or,
We're going to get there.
Okay, never mind.
But, yes.
You see what I'm saying?
Yes.
Okay.
All right, so looking here, remember products and reactants. If we have a small Ka, do we have more products or do we have more reactants?
Smaller.
If it's
Smaller, more reactants.
yes, so we have more reactants. So does it dissociate a lot or a little bit? A little bit, yes. Small Ka means less dissociation. The less it dissociates, the weaker the acid. On the other hand, if you have a larger Ka, you have more products, so more ions. So you're going to have more dissociation, and that's going to be a stronger acid. Note, the ER is important here. Stronger.
So it's not as strong.
It's not strong because it doesn't completely dissociate. If you can write an equilibrium constant for it, it's not strong. Most all of the Ks that are going to be given with regards to acids and bases are going to be in the form of Ka. We'll talk about how to deal with that. But you also have Kb, which is the base ionization constant. Same principle, but because I told you up here we already went over this multiple hydroxide groups, so I didn't write this with two different reactions, but the same principle would apply. So if you're going to write Kb, still talking about products over reactants, but here, when you have a Kb, you have to take into account the coefficient of your hydroxide. So you might have to deal with an exponent. This is why nobody likes Kb's. Ka's, acids only lose one proton at a time, so they are not coefficients over base. Again, water is a pure liquid, so it doesn't count. Or you can do conjugate acid, conjugate base, over the base. All right, we're almost done with this section, then we're gonna be done.
Is it the same way with the acid ionization? If you have a constant in front of it, then it'll be an exponent?
It would be, but acids only lose one proton at a time, so all the coefficients are gonna be 1.
Okay.
For these purposes.
So basically, acids don't have exponents.
Yeah, acids generally are not going to have exponents. So the same principle applies. Small Kb, less dissociation, weaker base. A larger Kb, more dissociation. Stronger base, but not strong. So which one is stronger? Hydrofluoric or hypochlorous? Hydrofluoric, because Ka is bigger. Notice it's still small, right? Yeah, still very small. But so we're going to be dealing with a lot of negative exponents here.